15.9, and I will start by giving you the concept on the Jacobian. Okay, so I will stop this presentation. Okay. And I hope today's internet is stable. I think it's still stable. Okay. Let me, yeah, still stable. Okay. Now, I've given you this this idea for 15.9. So hopefully, for the first 1 hour, I'm giving you all this concept, and maybe the last maybe 40 minutes or 30 minutes we will have some cues, an exercise. Okay, maybe 2 questions or maybe 3 questions we can solve together. Okay. So first, the chapter is the change of variables in multiple integrals. We have discussed last Tuesday that if we have a transformations, okay, let's say we have the axis is u, v, and then we have x, y, and it can be any functions. Like, well, for examples, it can be, for example, maybe u is y minus x, maybe y plus x, or maybe 2x plus y. It doesn't matter. It can be in any relation with u and xy, or v with xy, or yeah, something like that. And we can draw and then look at the difference, okay, from the original drawings, and then when it transformed to another axis. Okay, and that is actually the same idea when you are actually transforming the xy variables into r theta, into a polar. So from rectangle to polar, it's actually the same idea. And here is the difference, or the additional multipliers that we need to add to the polar, right? We need to add r here. Okay? This is actually called the Jacobian. It's from the Jacobian. And now I will going into more general. Okay, so what is Jacobian and how we can find the Jacobian? Okay, so let me draw. Okay, let me draw this v and then u, and then maybe draw a simple square like that. And then let's say this becomes delta v, and this becomes delta u. Okay, and we call this as S region. And the initial point here is the coordinate is u. Let me make here. The initial point is from u0, v0. Okay. So all the way here is v is constant, and all the way here is u is constant. Okay. It's u0. Okay. And then let's say we transform this into y, to xy, okay, into xy coordinates. And then maybe draw like this. Okay. Now we have here is the, let's say, the region R, and then this is the vector function R. Okay, the vector function R at u0 and v, and this is vector function R at u and phi0. And this will be the initial point, x0, y0. Okay, so we start with a small rectangle here with the point u0, phi0, and the dimension is delta v and delta u. And then we transform, and then the image of the region S in the xy plane is the region R. Okay, and then the boundary points. Okay, the boundary points. So we can write x, y, y0 transform. Okay, and then the vector function R, u, v, we can take into functions g in x-axis and functions h in y-axis. Okay. So this vector is the position vector of the image. Okay, so this is the vector position of the image. Vector position of image S. Okay. So we can also write the tangent vector. The tangent vector at the initial point x0, y0 to this image, okay, to this image curve is so we've partially derived with respect to u, okay, and we can also write this in terms of the Leibniz dou x dou u I plus dou y dou u j. Okay, and then we can also take the tangent vector for the with respect to v, and this will be g phi okay, and also this is dou x dou phi I plus dou y dou phi j. Okay, if we can imagine, okay, let's look this image R here. Okay, let's put this R, or let put this this image S into R, and what we can relate from there. Okay. Let me write maybe here. So let's draw the R. Okay, this is R. Okay, now this is the R u0 phi0. Okay, at the beginning, and this will be R, and this will be having plus delta phi, and from here it's having R. So this is actually the plane. Oh, I forgot to draw the tangent. So this is the tangent actually. Wait, let me draw here. Okay, so there is a line here, and let this line is B and this line is A. Okay. So we can approximate the R ds by parallelogram of vector A and B. So we need to take the area of the parallelogram, in which the parallelogram is to be defined by this A and B. Okay, and from here it is actually related to the limit definitions of derivative, right? So if you remember, the blue one is the secant, the B is the secant, and when you have uh, the delta, so when the delta is so when this delta is going to when the limit is approaching 0, then you will get the definitions of the derivative, right? And we can use that definitions, but first let me write that A is defined by R. Oh wait, A is plus delta U, and then minus, which means the difference between these factor positions. Okay, this A. Okay, and B is right. And then by definitions using limit. So first, if you look at the delta U here, this one, it's plus delta U. So when the delta U is getting 0, and this is by definition is the derivative definitions. So you need to minus the R, and this will be the delta. This is the definitions, right? And then from here, we will get that approximately that delta U RU will be equal approximately okay, and then doing the same way with the delta V approaching 0, you will get delta V RV is also approximately similar with the U, right? And then this is, by the way, the parallelogram that we want to going to look for. So this will be the parallelogram that we want to going to look. So this is A, right? This is A, this is B. If you remember the parallelogram, area of a parallelogram will be depends on delta U RU and delta V RV. So we can write this will be delta U RU cross the delta V RV. Or we can write this is RU cross RV for the factor, right? And this will be the delta, the rest. Okay, now let's compute this. Okay, based on what we have now. We have the RU is this, right? The factor, and RV is this. So let's cross these two. What will happen? So let me write here RU cross RV. Let me write I, J, K. And this would be delta x, dou x, dou u, dou x, dou v, or the v, RV, and this will be dou y, dou u, dou y, dou v, and this will be equal to 0 for k. Okay, now we can see from here, when I cross j, it becomes k, right? So it will be the determinant of this, okay? And since, okay, the determinant is this minus this, right? The blue minus the red. So this will be delta. Let me write delta x first. Delta x, dou x, dou u, dou y, dou phi minus dou x, dou phi, dou y, dou u. Okay, but since this part here is going to be the same, if you switch, we can also switch that, and that will be our uh, our Jacobian formula. So notice that you will have, if you write like this, you will have x, x, right? Y, y, and then u, phi, u, phi. Okay. Okay, let me write the conclusions in the next slide. Okay. So this is the determinant. Okay. And this is actually, the determinant is actually the Jacobian. Okay. Okay, let me write in a new page. So the definition, okay. So Jacobian of transformation T, okay, given by x as a function of uv, and then also y is a h functions also uv. This will be, we can write the terms for Jacobian is dou x y and then dou u phi. So meaning this is the transformations xy to uv, okay? And then by the formula that we have right before in the previous slide, you can write this is dou x, dou u, dou x, dou phi, dou y, dou u, dou y, dou v. Or you can solve this by uh, calculating the determinant. So by this Jacobian, we can put the Jacobian as in our delta A. So this will be the Jacobian. So we can have this is the area of the parallelogram, and you can relate this delta A. And let me make maybe a red box to make sure that you take notes for the Jacobian. Okay, and then from this Jacobian here, you get the delta A, and the delta A basically is what you are gonna use for the A here, right? If you have double integrations. So basically what we are going to do is we are going to input that. Oh, wait, I will start with the Riemann sum first. We are going to put that into our definitions by using Riemann. It's the same. And then we can exchange this x and y based on what we have done here in UV. So we can start write this as G UI VJ. Oh, sorry, it's VJ, and then H UI VJ. Okay, and let's put in the Jacobian here. And then this will be delta U delta V. This is practically the delta A, right, from here. So as a conclusions, suppose T is curve transformations. Let's say curve transformation whose Jacobian is non-zero, and T maps a region S. This is UV plane onto region R, that is the XY plane. And then suppose functions is continuous on R, and that R and S are type 1, type 2 regions, type 1, type 2 regions, meaning dy dx or dx dy. Suppose T is 1 to 1, so that you can inverse that, except perhaps on the boundary itself for the S. Then and you can write the Jacobian here. So this is the new double integral using the Jacobian. Okay, in practicality, actually Jacobian is not too difficult to use as long as you know how to connect the x, y, and UV. Okay? So, for example, the idea that I gave you before is you need to connect this xy with the r and theta, xy r theta. So first, okay, so let me write maybe here. Okay, so let's say we have x is g, and it's function of r theta, and we know that x is r cosine theta in the polar conversions, and y, let's say it's functions also r theta, and we know also this is r sine theta. Okay. Okay, we can start by track or check the Jacobian here. So write the Jacobian. So here is the dou x, dou r, and then dou x, dou theta, and then dou y, dou r, dou y, dou theta. Okay. Maybe here. Okay. Dou x, dou r. Let's see from the x and then differentiate with respect to r. This is cos theta. And then look for y and then differentiate with r. This will be sine theta. And look again for x and differentiate the theta. It will be sine, but negative. So we have r sine theta negative. And then the other one is r cos theta. And we now have the evaluations will be r cos squared theta minus so plus r sine squared theta, in which you have r, and r should be a positive terms. Okay, it should be a positive terms, and then that's why you have this double integral, and you want to rewrite this integral in terms of polar. This is what you get, right? You have the Jacobian here, and this is dr d theta, and the Jacobian is r, right? So that's why you are getting let's say this is alpha, beta, and a, b, and write all together r dr d theta. Okay, so that's how you are going to use the Jacobian. So Jacobian will be useful for finding relations in if you connect to any functions with different definitions. Okay, for example, you want to have a definition of other variables, and then you want to connect them to the xy plane, and you can also rewrite the xy into the other variables. For example, we are going to use u and v, right? In usual case here, we are usually getting to write u and v, but actually it can be any variables that you can write. Okay, so this is for double integral. Jacobian for the double integral. Now let me give you example, a few example, maybe one or two, okay? Or maybe one, and then we can move to triple integrals. We have r, and then we have x plus y divided by x minus y. This is dA. And R is trapezoidal region with vertices 1, 0, 2, 0, 0, negative 2, and 0, negative 1. Okay. So can you integrate this? I think difficult, right? So the way you are doing it is, first maybe I'm drawing what this looks like for the trapezoidal. So 0, negative 1 here, 1, 0 maybe here. Maybe let me draw. this. Okay, connect them there. Connect here to -2, -1, 1, and 2 here. Okay, we have this. This definitions. And then from here, you see that you can actually generate the line equation from here is x minus y is equal 1. And from here is x minus y equal 2. Right? Okay, now we can make, let me write here. So we can make change of variables. And suggested by the form, let's see the form here. We have x plus y and x minus y. So let's imagine the x plus y. Let this equal u and let this equal v. Okay. And then now solving these two for x and y, right? Okay, maybe first is you plus these two, so you have 2x equal u plus v, and you have x is actually half u plus v, and you have y with the same evaluation u minus v. So you have now these two equations of x with the variables u and v, and also for y. By doing this, we can actually make the Jacobian. And the Jacobian, though x, though u is just all is half, except for the last one is negative half, right? And check the determinant, it will be negative half. But since this term should be in a positive, so it should be the positive half. Okay. Okay, now look here. We have these definitions, right? The next thing is we have the coordinate, right? And we can now solve for the boundary. So if you look from xy, they have the vertices is from 1, 0 to 0, 0, -2, and 0, -1. Okay. And we're going to take this into a new approach that you need to take. So u is x plus y, v is x minus y. So from the first one, from 1 and 0, we get 1, and then we get 1, right? And from 2 and 0, 2 plus 0 is 2, 2 minus 0 is 2. Okay. And from here, x plus y, 0, -2, -2, x minus y, it will be positive 2, right? And the last one here, 0, -1. So plus, it's just -1. And then minus, it's positive 1. Okay. And you can actually draw this if you want. And look what the transformations is from this new coordinates for u and v. So this will be v, and this will be u. And we start from 1, 1 is here, 2 and 2 here, okay, and maybe connecting all together and become a new trapezoid. And we say that this is S. And the other one here is, let's say, R, right? Here, R from here, from the equation. And you have S now. Okay, and here you have also the line equations, right? So it depends on which one you prefer, du or dv, for your double integral. So let me write. This is r x plus y divided by x minus y, and then dA. So we can say that first, maybe write s. Okay. So e u over v, and this will be the Jacobian. So it should be positive Jacobian. So whenever you find a negative in your calculation, you need to convert it to put the positive. Let's say we want to evaluate du and dv. So write all and write half, and then du dv. So half is from our Jacobian here. Oh, sorry. Wait. Okay. So negative half. So take the positive one. And then if we want to take du dv, so we want to make v as a constant. So we can do it like usual in our double integral as usual. So this is, let's say this is 1, 1, 2, 2. Okay. So this is v equal 1, right? This is v equal 1. It will going up until equal to, right? Until equal to. So v will be 1 to 2. And how about the u? The u, because it's an equations and it has a slope, right? So we need to take the line equations, right? The equation of u is related to v. This will be u equal v, and this will be u equal negative v, right? So this will be start with negative v, and this will be v. And by doing that, you can basically solve this problem, because I think it will easily to be integrated, right? Okay. That's for the Jacobian, and how to use the Jacobian in a transformation process. Okay, hopefully you can do this kind of questions. Okay, so you have a functions that you need to double integral, evaluated by double integral, and you have a region. And the region, it can be defined by the, like, for example, this time is the vertices, the point, and you can draw the point. Or if you have the region based on maybe a boundary is some equations. Okay. All right. Next thing that is important is change of variables in triple integrals. So this is double integral. We still have a Jacobian in triple integrals. Okay. If you feel this too fast, please review in the recording. Okay, review in the recording. And if you have a question, you can just type in on the chat box whenever you feel maybe you need more explanations, you can type in. Okay. Okay. Next one is the change of variables in triple integral. Let me write that triple integrals. Okay. I will directly write if x is function of triple, let's say uv, and usually it's w. Okay. And then let me write the Jacobian first. And I think no need for statement of proof. Okay, I will write what is the Jacobian. So based on the pattern that you have from the previous Jacobian, the double integral, you have the same actually. So you need to just adding one more. That is the W here. Okay, and the rest will be the same. All right. So basically, you need to take determinant in 3 by 3 determinant. Okay, so this is the Jacobian. So Jacobian 3 by 3 determinant. Okay, and by using the same assumptions and hypotheses, we can also write the general equations for transformations. So you can transform R to S. So image. So S is the image of R. And then put in the Jacobian here. And that is the general formula for uh, Jacobian in triple integrals. The best way to understand the triple integrals or the Jacobian is the spherical coordinates. Okay, let me write the spherical coordinates. So best example, spherical coordinates. Okay, remember spherical coordinates, you will have rho sine psi instead of r. This is cos theta. Y is rho sine psi sine theta, and z you are having rho cosine. Sorry. Okay, and we have now changing x y z to rho psi or rho theta and psi. Sorry. Okay, let's try that as well. So let's write the Jacobian first. Let's compute Jacobian and prove whether it's the same amount of value or not. So I need to take that. Or maybe write the Jacobian first. So it starts from dou x dou rho. So we look for x and then differentiate with rho. This will be sine, psi, and cos theta. And then maybe it's too long. Maybe just there. And then the second one, the y is sine psi, and then sine theta. And then z is just cos psi. And then the next one is dou x dou theta. So we need to integrate theta. Okay, this will be negative because it's cos becoming negative sign. Write all like that, and then this is becoming positive and becoming cos theta. And z, because z there's no theta there, so it will be 0. Same thing for psi. We write rho because it's just positive, right? So we write cos psi cos theta, rho cos psi sine theta, and then negative rho sine psi. Okay, now that is our 3 by 3 determinant. And now let's compute, let's evaluate this. Okay, uh, first the giveaway that you can observe is this is having 0, so let's using this as our uh, a value to compute the determinants. Okay, because it's 0, so we need just these two, right? And compute this determinant, compute also this determinant, right? So let's start by writing the cos psi, and then determinant is negative rho okay, and then the other one is negative rho sine psi. It's take a while, but it's not too difficult. It's takes some writing, a lot of writing here, but it's not that difficult. So let's write the determinant is negative rho squared uh, sine psi cos psi sine squared theta. Okay, it's, the other one is minus rho squared sine psi cos psi, and then cos squared theta. Okay, and then negative rho sine psi. Here is rho sine squared psi cos squared theta minus minus, so plus rho sine squared psi sine squared theta. Okay, well, let's start simplify this form. So this will be cos psi, and then in here you will see that it has the same variables here, right? So we can factorize that. So it will be, let me write here, and we get sine squared theta plus cos squared theta, which is 1, and we can skip this and equaling this to 1. So we will write this only negative rho squared sine psi cos psi. Maybe going a little bit down here. And here is also, we have this similar case. Rho sine squared, we can write this as cos squared theta plus sine squared theta, right? And this will be equal 1. and then we can evaluate this, right? And we can write negative rho squared sine psi sine squared psi. Let me write like that. Okay, don't compute becoming q. And now we also have negative rho sine squared, same, right? And we can compute this and become this cos and cos become cos squared psi, and then plus sine squared psi, right? And so you have negative rho, oh, sorry, should be squared. And in Jacobian, you should take the positive one, so it should be rho squared sine psi. So that's why in spherical coordinates, you need to multiply with rho squared sine psi as the transformations. Okay, okay, that's it. For that's actually the last session on the 15.9, and I think we can go move to some exercise if you want. But before the exercise and maybe practice, maybe if you will have a question, you can write down the question if you have any questions. And maybe you can start uh, the exercise. Let me find the question for you. Mm, uh, mhm. Okay, maybe start with if we just finish off the Jacobian, maybe start with the exercise for Jacobian, and then maybe exercise from other section as well. Okay, let me write the question for you. Evaluate the value of double integral. And D is a square with vertices. So the question is asking what is this value? What's the value of the double integral? Okay, yeah, so you can start to work if you want. Try to find the answer. And while doing that, um, let me give you another maybe example as well. Okay, let's try number two also. I will go back to chapter 14. Maybe just refreshing your memory. This will be the answer is a little bit complicated, but I think good for your exercise. Or maybe we can have three questions. Let me give you another one. It's from chapter 15. Let E be solid, bounded by the sphere. And the sphere is x squared plus y squared plus z squared equal 4. This is 4. And bounded by sphere and cylinder. The cylinder is, let me write here, x squared plus y minus 1 squared. That's the circle equations. The question is volume of E is, okay. So, okay, I hope you can read the questions. If you want to, is it clear for the questions? Yeah, so you can start to work on these three questions. Maybe if we finish this, we can also add more questions. Maybe if you have find the answer for number one, you can write in the chat box. Okay, anyone find the answer? I think for number two is the answer quite complicated, but yeah, I hope you still remember the chain rule and the implicit differentiations also for multiple variables. Let me give you maybe 2 or 3 minutes, and I will give you the solutions. Okay, I will start number one. Actually that is the Jacobian. Okay, so remember, whenever you see any type, uh, for example, you see the idea of you have xy here, you have also xy here. Maybe the form will be a little bit different, but you know that if you want to integrate this directly from here, uh, that's quite difficult, right? So that's why one uh, one one solutions is to use the Jacobian transformations. And actually, if you are or if you can find relation in other application as well, you can use the same Jacobian transformations to write down the multipliers that you need when you need to transform. And it's actually useful. It's very useful for the application. Is actually if you want to use for analyze some data, maybe from the image of the process, like processing image, or maybe from I think some sensor, and you want to transform those information. Like when you have a data set, you need to transform from binary, and then you need to transform to from that code of binary. You need to transform to pixel, or maybe to some other set of data. You need to transform that, right? You need to transform the functions that are inside of that data sets. Okay, so first we can make some assumptions here. So let maybe u is x plus y, v is x minus y. It doesn't matter what relation you have here, as long as it is connected to the questions, okay, or to the given informations. Okay, solve this. Okay, solve x and y, right? And now you have, so if you are plus this or minus, right, you will get the relation between x and y for the solution. So you have x is half u plus v, and y is half u minus v. Okay, from here we have these vertices. We can check all these vertices, and we can write the uh, new set of equations. So u is, let me write here, u is x plus y, v is x minus y, and then we can write the new part of coordinates. So start from 0 and 2, start from here, 0, 2, plus become 2, 0 minus 2 becomes 0 minus 2, right? The 2 minus 2, right? And then start from 1, 1, it's 2 and 0. Okay. And then 2, 2 is 4 and 0. Okay. And the last one is 1, 3. 1 plus 3 is 4. 1 minus 3 is negative 2. So this is our new coordinates for u and v. All right. Now, because we already have these relations, we can also find the Jacobian. So the Jacobian can write like that. So we can just, because it's a simple formula, we can directly differentiate. It's become half. All will be half, except for the last one because it's having a negative. So we will have negative half. And find the determinant. It will be this, but because we need to have the positive value of the Jacobian, so it will be 1/2. And then we can plug in this Jacobian into our solution. But let me write this is d. This is x minus y, x plus y. And let me factorize half going here. And this will be a new v and u. This is v over u du. Let me make du dv. Okay. And if you look here for all these coordinates, you can check what it looks like in the uv. So it starts from 2 and negative 2, maybe going down here. From here, this to negative 2. And then another one is 4. 4 is here. So let's start from this 4, 0. 4, 2 is 4, negative 2 here. And this is 2, 0. So we will have a square. And because it's square, we don't really need any equations that are defined on that u and v, right? So we can write, so from v, v is from, let me write, this is u, this is v. So v is from negative 2 to 0, right? So we can write v is negative 2 to 0, and u is from 2 to 4. Okay, now the next thing is we can integrate. Oh, notice that you can actually reverse this as long as you want. And the idea for reversing the integral is to help you solve the calculations, right? And if you look here, it's 1 over u du, but because it's easy to integrate 1 over u, it's just ln, right? So you can definitely just stay as it is, but sometimes maybe you need to reverse. So it will be v and then ln u. We put in 2 and 4, and then dv. Okay. And this will be half, and v, and ln 4 minus ln 2 dv. Okay. Okay, remember, in ln, you can write like this, right? And then you can write this, which is ln 2. Okay? So we can write this in terms of v ln 2 and dv. And then we can integrate v, become v squared over 2 and ln 2. Integrate from 0 to negative 2. The first one is 0 minus 4 divided by 2 ln 2. It should be negative, right? Negative 2 ln 2 and multiplied by half, it's negative ln 2. Okay. That's for the first equations, the first questions, right? Okay. Any questions from the first one? If not, let me look for other case if there is other. Okay, maybe we can move to the second questions. Okay. Okay, so that is one example. The second questions is you need to find this dou z dou x. And how you're going to do that? First is, basically this means, if you remember implicit differentiations, so this is basically telling you that if you have, or if you differentiate with respect to x, then all the variable x you can easily differentiate, and you can also differentiate the variable of z, but you need to add the the partial forms. Okay, so let's start here. So let's write this and differentiate with respect to x. Okay. Okay, as I mentioned, when you are taking z here, l and z, you need to differentiate z because that is our goals here. So first, this will be uh, ln will be 1 over z, right? Or you can write, make it easy, write 4 into front of ln, and you can write 4 over z, and then dz dou x, dou z dou x. Okay, and then here you have x and z, right? You need to do a product rule. Okay, to do a product rule, so plus first is I will differentiate x, so it will be 7yz, and then the second one I will differentiate z, and then plus 7xy dou z dou x. Okay, and then equal, this is also the same. We need to have a product rule here. So product rule, this will be 2x d, and then plus integrate, differentiate the e to the z is x squared ez, and then don't forget the dou z dou x. And then simplify, and then combine all. This is x, y, and then let me combine with the other here, the x squared, and then it's equal, and then the answer is just finding this, right? So this divided by this, or yeah, and then you get the answer, and you need to look for the options if the question provide the options. Look for this options here. Okay, I believe it's not really difficult as long as you are careful when you did all the partials. Well, let's move to this other question here. Let E be a solid, okay, and then bounded by sphere x squared plus y squared plus z squared equal 4, and also bounded by the cylinder. Okay, now this is quite interesting question. Okay, uh, so first is you have a sphere. Okay, so all the region of E is inside the sphere. Maybe I can help you to take a look by drawing. Okay, let's say that is our sphere. Okay, and then we have the cylinder. Cylinder. Let me write here. Cylinder is x squared plus y minus 1 squared equal 1. Okay, this is a circle equations. And if you look here, this it is having the center at 0 and 1, right? So if you have circle, if this is xy plane, circle will be here. So this is the center. Okay, okay, I hope you get the idea. So circle will be here. And it takes some height here, if you can imagine that. It will form a cylinder. But the interesting part is it has the radius of 1, right? R is 1. So this is R, right? But the radius of the sphere is 2. So it's quite interesting in terms of the forms, right? Okay. So if you look only at this xy plane here, so this is saying that the region in the area here for xy plane is basically the maximum that it can take is only 1, right? Okay, to help you to take the multiple integrals and find the volume of E, so basically you need to have this E and then this dV, right? And that is your volume. We need to define our E. Okay. First is, if you want to have Z here, we can take Z from the sphere. So if you look here, you can take Z from sphere equations, and you can take this as your Z. So the upper lower is the positive, the the upper surface is the positive, and the lower surface is the negative. Okay. Okay. Now for the double integral, okay, for the double integral, we can use the polar. We can use polar coordinates. So we need to transform this into polar. So write in polar. That will help. Okay. So first, in terms of polar, imagine that this is on polar. Okay? The circle is on polar. And imagine that if this is 0 degree or 0, the angle is 0, theta is 0. This is theta is pi over 2. Imagine that. And this is theta is pi, right? So we now have theta is from 0 to pi. Okay. So we can write maybe here, theta is from 0 to pi. And how about the r? Well, because we can convert from the cylinder to polar, from this cylinder equation to polar, then we can write uh, x is r cos theta. So we can write r squared and then cos squared theta and then plus. Okay. Let me expand this into y squared minus 2y plus 1 and convert this into a polar. So y become r sine. So r squared sine squared theta. Okay. And then minus 2r sine theta plus 1. And it's equal 1, right? This will be canceled. And this will be r squared, and you have this equations, right? Remember, okay? Whenever you have this quadratic equations like this one, do not take this equation as, and maybe you feel that, okay, I can cancel this, okay? This is wrong, okay? Because in quadratic, it's squared means you may have options for r, right? It's not exact 1r, the answer. So you need to take this r into, you can factorize, and this will be this. So you have r equals 0 and r equal to sine theta. So r can be 0. That's the problem. So this is wrong way. This one, okay, wrong. So you need to do these factorizations. Okay, so that is our r. So from here, from z, we can take this plus minus 4 minus r squared. Okay, so we can take, first is z. So this will be dz, r, dr, d theta. So we can have a cylinder, right? And r will be from 0 to 2 sine theta. And theta will be from 0 to pi. Okay? And then we can take the integrations. Okay? I think for theta, we can take that integrations and write as pi. And then r, let me write just r. And let me finish the z first here. So it's becoming z, right? zr. So zr dr, and it has negative 4 minus r squared and positive 4 minus r squared. And then we can plug in. We can plug in this value. If you plug in 4 minus r squared, square root minus square root of 4 minus r squared, minus minus, so it has positive, so it will be 2, right? So I can write 2. Let me write r, and then we have 4 minus r squared, and this will be dr d theta. Oh, d theta, I already count for theta. And I believe you can check this out. Oh, wait. I think I made a mistake because it's a functions. I need to take this one by one. Sorry, my mistake. Okay, so first take this integration first. Okay, so why I need to still write this, not integrating with theta, because I have this. Okay, that's the problem. Okay, take u sub. And then it will cancel, right? It will cancel this 2r, and it will be minus. And then let me write here. So it will be integration of square root of u, which is the 2 over 3 u with 3 over 2 power. So we will have 2 over 3 minus 2 over 3, and then u is and plug in 2 sine theta and 0. And you can try to finish off this, right? Okay, I think it has some steps for finding the solutions, but in the end, by using some, I think just u sub method all the way. So here's u sub, and when you plug in sine and integrate, I think you need also u sub, and I believe you will get the solutions afterwards. Okay. Um, I think we still have time. I can give you another one. Mm, okay. Let me move to the next one. Okay, if you have E, now it's 3 variables like that. And then it's from then this is E. Okay, that is the questions. So what is this if E is already defined as like that? Maybe two questions for you. The second one from here is surface area over disk this of circular paraboloid z equal x squared plus y squared is. Okay. So second question is about surface area, which is in this 15.5. If you remember that. Okay, let me give you a couple of minutes, and maybe I'm giving you just a clue how to deal with this exercise. Okay, let me give you the idea behind this exercise. Okay, the first question here, if you look this sort of questions, it has these questions, this equation here, right? It's also similar to the questions asked. So by the information here, you know that this is a sphere, right? Which means you can use the spherical um, equation, spherical coordinates equation, right? So this will be telling you that the row is from 1 to 2. The radius is 1, right? To 2, right? So radius is from 1 to 2. And how about the other angle? So if you remember the sphere, let me draw the sphere, okay? Because it doesn't tell you anything else aside from this sphere. So first, the theta that is in the xy plane here, it will be in the whole circle, right? And the angle psi on the on the z-axis here is pi, right? So all details will be put in. So psi is pi, and theta is 2 pi, the full circle, right? Okay. And then you can write this E in terms of spherical. So write this, so we can change this to rho squared. And then it's having 3 over 2. Okay. So we have rho cubes. And then don't forget, whenever you take conversions to sphere coordinates, you write the Jacobian, right? The rho squared sine psi, the multipliers, and then dou rho, dou psi, dou theta. You can write dou theta or dou psi. If both are constant, they both will be um, okay to be reversed. So right here, 1, 2, 0, pi, 0, 2 pi. Okay. And I believe this is, you can take this easily because this first one here for for rho, you can take this using u sub, right? And then later sine psi, differentiate, integrate, and then become a negative cos, right? And then later the last one is just adding 2 pi. I think not too difficult to be take these solutions. Okay. The other one here, the surface area. Remember, okay, I will give you the general equation. The surface area will be, so will be 1 plus partial x squared and then plus partial y squared. And then let's say this is dA. And the area is this, the x squared plus y squared. Okay. So we can write this in terms of x squared plus y squared less equal to. Okay, now we can take the partial x first. That is just 2x. Partial y is just 2y. And then take the squared. This is 4x squared. This is 4y squared. And then plus 1. So we have 1 plus 4. This is x squared plus y squared. Okay. And by looking at this equation here, you know that this x squared plus y squared we can convert to polar because it's a circular equation. So this is r squared. And by doing that, we need to convert this to dr and d theta. And because it's only a circle and there's nothing else to be provided there, we just assume that it will be a full circle. And the radius is and of course you can easily integrate, and from here you see that you can also use u sub, and then the rest is just regular integrations. Plug in the value and then you get the answer, right? Okay, I'm giving you the hint, and I try to work on uh, the the solution for all of these exercise. Okay. Okay, so for the survey, okay, there's a new one. Anyone haven't filled in the survey? I will announce the official announcement tonight. But from what I've seen now, uh, I think that this it is easier to have on Saturday because some of you are having like some is Wednesday, some is Tuesday and Monday, and others having additional course in between Thursday and Friday. So I think maybe Saturday is okay. But I think a few of you have a final also on Saturday, but it's on the morning. So I will take our course in the maybe 3 p.m. around, or maybe 3:20. We will have approximately around 2 hours 20 minutes, or maybe 2 hours 15 minutes for our final. And don't forget to set your device for the Google Meet and device for opening the Google form. Okay, and it will be also auto close for the Google form. So uh, you need to be careful on that. Okay, and I think I also give you sometimes to scan your documents, to scan your paper. Okay. Okay. Any questions? So as far as I receive your survey, it will be Saturday. Okay, it will be Saturday. Our final will be Saturday. Okay. Any questions? And also, please wait for tonight. I'm putting some maybe some exercise to help you. Maybe just 10, 11 questions to help you to work on, especially the last subject, chapter 15. Uh, it's the review part, and I check chapter 15 review. It's the same for all editions, I think, from 7, 8, and 9. So if you use the 9 edition and working on the same number for the review, the result will be the same. Okay, so it's different from the last time. Last time 15.2 is the 9 edition having more subject, and I'm attaching the different edition. So sorry for that. Okay, but you need to refer to what I'm attached. But if you just use the book, I think that's okay. It's the same question. I've checked already, so you can check that exercise, and uh, you can try to work on that exercise, and I will see your work, and maybe on on this weekend I will put the solution for those exercises. And if you have any questions aside from that, please let me know. You can email me if you want. And yeah, this will be the end of our lecture. So yeah.